The topic that we're going to cover in this unit is on functional groups. Functional groups are going to be groups of different atoms within molecules, and those groups of atoms are going to have particular functions in terms of the types of reactions that molecules will undergo. And that's why we name them functional groups, is because the structure of these groups, that is what atoms are there and what order they're arranged in, are going to dictate the function of that portion of the molecule. And when we say the function of that portion of the molecule, we're talking about what types of chemical reactions it will undergo. We might be talking about what types of biological targets it could bind to and interact with, and things of that sort. So functional groups, what we're going to be looking at are some common motifs that we will see of atoms, or common arrangements of atoms. So we're going to look at common motifs of bonded atoms. And it's really important to be able to recognize functional groups within molecules, because oftentimes in an organic molecule, we're going to have several different functional groups, or several different regions of the molecule that have different types of atoms that are present there and bonded together. And those different regions of the molecule would have different types of chemical reactivity, and we can predict the chemical reactivity based on what functional groups are present there. So they're going to be functional groups are going to be motifs of bonded atoms, and we can use functional groups to predict the types of reactions that the molecules will undergo. And one of the things that's going to become challenging as we get into the nitty-gritty of organic chemistry is that there's an awful lot of different chemical reactions, and we need ways to help us classify those and categorize those and keep track of all these different reactions that we're going to be looking at. One way that you can use to help you keep track of them is to recognize different functional groups and know that if there's a functional group present, that it will undergo a certain set of different types of chemical reactions that are unique to that functional group. So we need to be able to look at and recognize different functional groups within molecules so that we can start to look at the types of reactions that they will undergo. So on the website, there is a list of the functional groups that you will need to know for purposes of this class. The ones that you will need to know are the ones that have the stars next to them. The other ones are ones that are more relevant for organic chemistry 2 or other classes. And I do want to add a few things to this list, or highlight a few things on this list to get you up and running on the different functional groups. So first things first, in order for the molecule to be defined as having a particular functional group, it absolutely has to have everything that is listed under this heading of functional groups. So for example, for a molecule to be defined as an aldehyde, it has to have both this carbon-oxygen double bond and then directly attached to it a hydrogen. So it absolutely has to have that. The line that goes off to the left that has nothing listed there can be whatever you want. And sometimes that'll be listed as just the letter R for an R group representing just a generic group of whatever might be there. As we come down, similarly, people get confused with amides. Amides also have that carbon-oxygen double bond, but directly bonded to the carbon-oxygen double bond has to be a nitrogen. That nitrogen has to be directly bonded to the carbon that's double bonded to the oxygen. Then those lines that go off to nowhere are lines that are running off to whatever. They're running off to different R groups. So I could plug in R, and R, where R is defined as a variable. It's whatever group that you want to be there. What actually absolutely has to be present for a molecule to be referred to as an amide is that it absolutely has to have a carbon-oxygen double bond directly bonded to a nitrogen. You're going to see a bunch of different molecules that have this carbon-oxygen double bond showing up, such as a carboxylic acid has a carbon-oxygen double bond, and that carbon is directly bonded to an OH group. An ester has a carbon-oxygen double bond, and then that carbon is directly bonded to an oxygen that's directly bonded to another carbon. So anything that's shown in this chart explicitly are what parts of the molecule absolutely have to be present there that can't be variables. The lines that go to nothing are what can vary from one group to another. So we see that carbon-oxygen double bond showing up quite a lot in a variety of different functional groups. And there is a special name that we can use if we want to refer to just the carbon-oxygen double bond portion of the molecule. So if we want to refer to just a carbon-oxygen double bond by itself, we refer to that carbon-oxygen double bond as a carbonyl group. And that is a word that I definitely expect you to know, because we're going to be referring to a carbon-oxygen double bond as a carbonyl group throughout the semester. This is like learning a second language in many ways. This terminology here, when I say the word carbonyl, what you'll need to have in your mind is that that's a carbon-oxygen double bond. So there are multiple functional groups that all contain carbonyl groups. Examples include aldehydes, amides, carboxylic acids, esters, the ketone, which is one that we haven't highlighted so far that has a carbonyl group, and then on both sides of that carbonyl group are carbon atoms. They absolutely have to be present there for the molecule to be classified as a ketone. And there's others as well that are not covered in this sheet that are a bit beyond the scope of Organic Chemistry 1 that all have that carbonyl group. So you should be able to recognize that. And this terminology of functional groups is important not only for being able to predict what types of reactions different groups within molecules will undergo, but it's also important for looking at a massive molecule, such as a drug molecule, and we want to point out a particular region of the molecule. We could point out that particular region of the molecule by referring to what functional group is there. So I definitely expect that you will know all of the functional groups that are highlighted with stars. So there's stars on several of these going down. I expect that you know all of those by memory for exams, quizzes, and everything else. And one way to help yourself in mastering these, because there is quite a bit of information here, several of these that you need to learn, and some of them are pretty subtly different. One strategy for this is to make flashcards, where on one side of the flashcard you put the structure of the functional group, on the other side you put the functional group name, such as alcohol is an OH group. And when you're picking out what functional group a particular molecule meets, keep in mind that you want to go with whatever encompasses the largest number of atoms. So for example, you might have some confusion if you look at a structure that has, let's say, something like this. You might look at this molecule and you might say to yourself, oh, well, there's an alcohol group in this molecule because it has an OH group. And if I go up here to the alcohols have an OH group. But keep in mind that we want to go with whatever motif, whatever group matches the largest number of atoms here in this group, and that's not going to be the alcohol. Instead, the largest number of atoms we have a match in the template for is going to be the COOH, our carboxylic acid group, which is the one up here. So we describe this molecule as being a carboxylic acid, not an alcohol. So I'm just going to put alcohol here and draw a giant X through it because this is definitely not an alcohol, but that is a common mistake that people make when they're starting out, is they look for whatever the simplest thing here is that matches the group they have in their molecule. And what you really want to look for is what the most complex thing is that's an exact match. It has to be a perfect match. So one example of a place where people get tripped up about things that are perfect matches versus not perfect matches are they might look at a molecule that looks something like this. And you might be asked what functional groups are present here in this molecule. And so one thing that people might look at is they might say, oh, there's a carbonyl group and a hydroxy group. Therefore, it's a carboxylic acid. No, no, no. For it to be a carboxylic acid, the carbonyl group has to be directly bonded to the OH group, just like we see right here. It has to be a perfect match. And that's not the case here. So instead, what we would describe this molecule as being is we describe it as being a ketone, having a ketone group, because a ketone was defined as a carbonyl group directly bonded to two carbons. That ketone was right up here in the second column. And then as a separate functional group within the molecule, we have over here this hydroxy group. A hydroxy group is an OH group. OH groups are the hallmark of alcohols. So we could describe this as an alcohol. Definitely don't describe this molecule on the lower right as being a carboxylic acid. It's not a carboxylic acid because it doesn't match the carboxylic acid pattern perfectly. It has to be a perfect match of the pattern that we see for the molecule. So let's take this information and throw out a couple of more definitions or a little bit more fill-in information here to help you sort out things. So an aldehyde group, where we have a carbonyl group directly bonded to a hydrogen, a common way to abbreviate that is rather than showing it all explicitly, we can do a condensed structural formula that by putting CHO. So if you see the term CHO within a molecule for a condensed structural formula, you automatically need to know that the structure that corresponds back to is the aldehyde structure. And this is another thing that you could perhaps help yourself in getting down by putting on flashcards. We have CHO on one side and the aldehyde group on the other. So CHO will always represent an aldehyde group. On the other hand, another common abbreviation that we will see is the abbreviation for a carboxylic acid group, which is COOH. So be aware that if you see the term COOH, that implies that the structure, the Lewis structure of the molecule would be a carboxylic acid group, a carbonyl group directly bonded to an OH group. And those are things that you just really have to commit to memory, because at first it may not look intuitive that COOH equals a carbonyl group bonded to a hydroxy group, but it does. The other item that I want to add to the list here of different molecules that you will be responsible for, different functional groups, is on the list we do not see what's referred to as an aromatic molecule. An aromatic molecule is one that you should add to the list and add to your flashcard deck or however you're planning to learn these. An aromatic group is a group that has a six-membered ring with alternating single and double bonds, and it's commonly abbreviated as a hexagon with a circle inside of it. And the reason that there's a circle inside of it is because if we were to show resonance going on for this ring, we could show that we can move the pi electrons over to here, these move over to here, and this moves over to here, all without violating the octet rule, showing that those electrons can actually be located in multiple places within the ring by resonance. And so to reflect that those electrons are actually not physically locked into those places, but instead by resonance, they're actually all around the ring, we use that circle inside of the hexagon to reflect that. So if you see a hexagon with a circle inside of it, that's going to represent a six-membered ring. And we refer to that six-membered ring with alternating single and double bonds. The functional group that it falls into is referred to as an aromatic functional group. So this is an aromatic group. And in addition to the functional groups on this list, which again, you can pull this list off of the website under Files. In addition to what's on this list, I do expect you to certainly know that an aromatic molecule refers to a six-membered ring with alternating single and double bonds. That's going to be the definition that we'll go with for that. So let's try to apply this information on functional groups toward an example problem here. So the example problem that I'm going to pull up, and if you're not super interested in drawing out this relatively complex structure, this structure is provided in the packet of information that goes along with functional groups under Files on the website. So if we take a look at this structure, this is not a structure that I just made up. It is a structure for erythromycin. And no, I don't expect you to be able to spell erythromycin. Erythromycin is a relatively commonly prescribed antibiotic. And we're going to go through and try to pick out the different functional groups that we can find within the structure of erythromycin. So this is going to be an example problem to get comfortable with picking out different functional groups. We're going to highlight the atoms that make up that particular functional group, or circle the atoms that make up that particular functional group and label it. So what you can really look for when you're looking for functional groups is you can look for heteros, non-carbon, non-hydrogen atoms, as sort of a starting point for finding the different functional groups. That'll lead you to a lot of the low-hanging fruit here. So starting at the top, I see a carbonyl group, and that carbonyl group is directly bonded to two carbons on both sides. And so looking back at the chart, we see that that matches up perfectly with a ketone. So I'm going to label that in as a ketone group because it's a carbonyl group directly bonded to two carbons. If you refer back to your sheet, you'll see that a carbonyl group directly bonded to two carbons is a ketone. If we come on over and go around the system, you could label much of this as an alkane, by the way, because it's carbon-carbon single bonds. I'm pretty much omitting that, but certainly there is alkane present there. We have a hydroxy group directly bonded to a carbon. We don't have a carbonyl group or anything like that adjacent here, so we just describe this as being a simple alcohol molecule. Then we come onward through the system. We come over to here, and we have carbonyl group directly bonded to an oxygen that's directly bonded to another carbon, and this carbonyl group here directly bonded to another carbon. We come up and we look for what has a carbonyl group directly bonded to an oxygen. And we see in our chart carbonyl group directly bonded to an oxygen. We can narrow that down to a couple of possibilities out of our list. One is the ester, and one is the carboxylic acid. So we have to ask, what is that oxygen bonded to? Is it bonded to a hydrogen, or is it bonded to another carbon? And if it's bonded to another carbon, it means it's an ester. And indeed, here, our Oxygen is directly bonded to another carbon, so therefore this group is an ester group. Going onward through the system, we can point out a couple of additional alcohol groups here. So there's an alcohol functional group right here. I'm labeling all the alcohols in blue. There's another alcohol functional group right here. Be careful when you're picking out alcohols that you're actually picking out alcohols and not carboxylic acids. If there's a carbonyl group next door, it's going to be a carboxylic acid instead. But these are definitely alcohols. There's no carbonyl group next door. Then we come onward to this funky functional group right here. Carbon directly bonded to an oxygen and bonded to another carbon is referred to as an ether group. An ether group was not one of the ones that we looked at specifically before, but if you take a look through this list here, our ether group right here in the second column, I'm circling it a bunch of times in green there for your reference, carbon, oxygen, carbon as the motif there. And so we'll describe this group as an ether group. We actually have several ether groups in this molecule. Ethers are relatively common amongst drug molecules. We have another ether right here because we have carbon that's part of that six-membered, six-atom ring, oxygen, carbon. We have an oxygen atom here that's bonded to a carbon and bonded to another carbon. So all these groups that I'm highlighting in green are ether groups. Another ether group right here, carbon, oxygen, carbon. Another one here, carbon, oxygen, carbon. We're just finding the patterns. Recognizing the patterns is the key here. So those are all in green ether groups. Found another alcohol right here because it's OH group directly bonded to a carbon. So we're good to go on that. Found another alcohol group over here. I'm highlighting all the alcohol groups in blue. And looking onward at the ring, do we see any other heteroatoms that we can pick out here? And I do indeed see over here a nitrogen. So the nitrogen can be part of either an amine group, AMINE, or an amide group, AMIDE. And if we look back at what differentiates an amine from an amide, we'll see that an amide is a molecule that has to have a nitrogen directly bonded to a carbonyl group. The amines, on the other hand, which we classify as primary, secondary, or tertiary, all have just a nitrogen atom that is not directly bonded to a carbonyl. So definitely get down clear what's the amide versus the amine. And the difference between primary, secondary, and tertiary amines is how many hydrogens versus other atoms each is bonded to. So primary amine is bonded to one non-hydrogen atom. So we see that one bond going from nitrogen to elsewhere. So it's primary, meaning first, it's bonded to just one other atom other than a hydrogen. Secondary means it's bonded to two other atoms that aren't hydrogens. Tertiary means it's bonded to three atoms that aren't hydrogens. So there's three lines there. So primary, secondary, and tertiary amines are ways that we can classify the amines. So if we take a look at and zoom in on our nitrogen atom right here, and we look at how many hydrogens it's bonded to versus other atoms, we can classify this as a tertiary or third degree amine because it's bonded to three non-hydrogen atoms there. And it's certainly an amine, not an amide, because there is not a carbonyl group next door. If there's a carbonyl group next door, then we describe it as an amide instead. So looking at our structure here, we're pretty much down to all that would be left here would be what we describe as alkane groups, meaning carbon-carbon single bonds. We've established the rest of the functional groups within this erythromycin molecule. So you can see in a complex molecule like this, if you wanted to refer to a specific portion of the molecule, it'd be really useful to be able to use the functional group terms. If you wanted to draw, for example, someone's attention to the ketone group, you could easily draw their eye to that top part of the molecule there that we've highlighted in red, or you could draw them to the tertiary amine group in the upper right corner of the molecule, or there's several different alcohol groups that you could draw the viewer's attention to. So functional groups are really useful as terms for identifying different parts of molecules, and they're also going to be really useful tools when we get into chemical reactions. So now is the time to master these.